So welcome back to this session of CFD. So in the past sessions we have checked or gone through the upwind concepts and numerical discretization. So now we'll be going ahead with pressure velocity coupling, again a very important topic. So all topics from now are just important. So from mesh to numerical discretization, and then the upwind concept, and now the pressure velocity coupling. So let's just write that: pressure velocity coupling. So what is it? Um, okay, so in the momentum equation, right? I'll just give you a background. In the momentum equation that we use, so here it needs pressure, right? Needs pressure, and the continuity equation continuity equation gives no pressure, no pressure, right? So you can just assume it, not assume. So the momentum equation, I have told you how it looks. The continuity equation is just d rho by dt plus del rho v is equals to 0, right? So this is your continuity equation. So here you can see there is no pressure term that's involved. So and here you have a del p term that's involved in the momentum equation. So you need the pressure term in the momentum equation, but you don't get the uh, pressure term from continuity equation, right? So that's why we need to have a coupling between both, that is the pressure pressure and velocity, right? I'll explain it in bit detail. So assume there's a flow of water, right? And so you use the momentum equations, fine, and you have some value of u1, uh, v1 and w1, right? Now when you put that in the continuity equation, it's not necessary that it satisfies the condition, but if I am taking a practical flow, the velocity that I'm getting from the momentum equation and the velocity that I'm getting from the continuity equation, that is u1 v1 w1, from the continuity equation, both should match, right? So what is the thing that controls both of them? Exactly, it's pressure. So these velocities depend on delta p, that is pressure, because the momentum equation consists of this term delta p, right? So if I have to say that I have to adjust values of u1, v1, w1 such that it is same, such that it satisfies the continuity equation, then what is that control factor? That is your pressure. So that is why it is very important to couple pressure and velocity. So pressure is like a correction term for velocity, and velocity that is required to solve the equations. So I'll just explain again why we need the coupling. So let's say the continuity equation, let's take the momentum equation. So that is your dou rho v by dt plus del rho v plus is equals to dou p by dx minus dou p by dx plus some source term plus any such term, okay, the diffusion term. So now this term here, the pressure term we have, but you need the velocities, right, in order to find pressure. And in the continuity equation, that is dou rho by dou t d rho by dt plus your uh, del rho is equals to 0, right? I'm sorry, this is not del rho v, this is del v, and here it's del v. So this is equals to 0, right? So you cannot find the pressure over here directly because it's related to velocities. So what you have to do is, when you guess a pressure, then you find velocities, and then you put it into the continuity equation, and you check how far it is from satisfying the continuity equation, and then based on that you correct the pressure. Why? Because the factor that is controlling the velocities here is pressure. So you change pressure such that your velocities are modified, and then you keep iterating it into the continuity equation such that this equation is finally satisfied. So this is what, or why we call it as pressure velocity coupling. So without each other they are incomplete. You cannot calculate any one term, right? Because you just cannot calculate velocity alone, because the controlling term is pressure. So unless you have pressure, you cannot just alone calculate velocity. Because at different conditions there has to be something that controls flux, and that uh, something that controls flux is your pressure, right? So okay, moving on. So we'll just look at what staggered grids mean. Staggered grids. Okay, so the idea of all this now come from the theory that you have mesh elements or control volumes. So this is, let's say, my control volumes or cells, right? So normally what initially happened was, you had pressure, velocity, everything stored in the center of the cell itself, right? So let me see, P1, U1, W1, V1, 2. So I'll just take this 1, 2, 3, 4, 5, 6, 7, 8. So let's say for each of the cell, right, the values were stored within the cell center. Now the problem with this is that, let's say you have this condition, that is checkboard pressure. Okay, so checkboard pressure is something where I have alternate pressure oscillations. So let's say like 1 0 1 0. Okay, so I'll just draw the cell. So you have 0 1 1 0 0 1 1 0. So this is a checkboard type of pressure. So it's just like a chessboard, checkboard, whatever you call it. So you have 1 0 1 0 1 0 1 0 1 1 0 1 0. So this alternate rising and falling of pressure. So here now these are the uh, pressure at the centers, right? So I have to find at, at the face. I can say it is, let's say, the average. So average 5. So 5. Okay, so it's this 5 is pressure over here, right? So the I'll call this as E, P, and G. Let these faces be E, P, and G. So the pressure at E will be equals to the sum of the average of pressures, that is 1 plus 0 by 2, that is 0.5, correct? Now I am taking the pressure, I am finding the pressure at this face P. So 5P is equals to, again, average, that is 0 plus 1 by 2, that is 0.5. Okay, now you might ask, why are we not using the upwind concept? Well, you can, but for suppose I'm taking a flow, right? Velocity. Now, if I use the upwind concept, just imagine. So if I'm using the upwind concept here, the pressure will be based on this. That is, it will be 1 itself. But now if I reverse the flow, I'm finding the pressure over here, same point. What will you get? That is 0, because the flow is now from. So when you're going from this here point P to point Q, point E, you are having 1 as the pressure at the face. Okay, because it was 1 here and 0 here. Now the flow is this side. So it's upwind concept, it goes the opposite side. So from E to P. So now you go the reverse. So it was 0 here and 1 here. So now the pressure at face is 0. Now just think logically. Is it possible that suppose you have water running inside the pipe, now you are just flowing it from the opposite side, right? The pressure at that point shouldn't change, right? So at one I mean at one time you're getting one, and when you're reversing the flow you're getting zero, according to the upwind concept, right? So it is kind of illogical, right? So that is why here we are just going with the average right now. Okay, so that doesn't mean that upward concept is wrong. It just at some places you just cannot apply it. It's just a logical fallacy. But yeah, see, this is one. That's why the checkboard pressure is one of the exception cases that we take. That's why you have different types of grids, right? So it doesn't mean that the upward concept is wrong. It's just that you need some corrections, right? So yeah, that's where we go. So yeah, so here as I told, at this point, at this phase, you have got 5e, that is pressure. You have got 0.5. So at the pressure at E is equals to 0.5, and the pressure at P is also 0.5. Now, if I have to find the velocity of flow, right? So just imagine that this was the pipe, and this whole grid is technically just this flow. I want to find the velocity of flow. So you know that velocity is directly proportional to del P, right? You can say it's momentum equation or Bernoulli's equation, whatever you remember it. But yeah, we are taking standard as the momentum equation. So velocity is directly proportional to del P, or the change in pressure. Now here if you see, you can see that the pressure difference is going to be zero. Why? Del P is equals to PP by minus PE. This is equals to 0.5 minus 0.5. So you're going to get 0. Well, what does this mean? If velocity is 0, technically it means that there's no flow. But is that possible? Of course not. There should be flow, right? It's just that the pressure is alternating. It doesn't mean that there is no flow of water. How can there be no flow of water and or how can there be no velocity at all, but pressure keeps changing? That's just not possible, right? So that is why uh, that checkboard the checkboard pressure case is one particular case that we have to account for. So that is what the normal grid was. So that's just the normal grid, right? What we talked about. So when you take the normal grid, you take a case of so yeah, so we checked at the checkboard pressure. So the checkboard pressure case. So because of this, you cannot have data or everything, that is pressure, velocity, uw, all stored at center, because it will cause this case where you get your v is equals to 0, but p is alternating, that is going up and down, alternating, which isn't practically possible, right? So this was up with the normal grid. So what scientists came up with, or engineers came up with, is what you call the staggered grid. So the most famous one is the Harlow Welch staggered grid. So what is this? So as I said, in the normal grid, you had velocity, pressure, and all parameters stored in the cell center itself, right? So here now you are playing a different game. So you have velocities stored at cell edges. These are just notations. I'll tell you once I complete it. So yeah, so your squares, are, let's say, u velocity, or let me say like v velocity, and your circles are u velocity, and your star is pressure. So what does it mean? you don't have to remember all this. You just have to remember that the pressure is stored at the center and velocities and rest of the parameters are stored at the edges or the faces of the cell. So now what does this do? So here now it completely removes the occasion of the condition of checkboard pressure, because now you have you directly have the values at the faces, right? So when you're calculating for velocities, you directly take from the face over here, and that is why it is this this configuration was accepted in the late 1900s. So yeah, so that was about the Halo-Welch staggered grid. So as I told, now since the velocities are directly stored in the faces, you don't have to do any interpolation. In the normal collocated grids, you used to use like phi p is equals to sorry, E is equals to, you'll say phi p plus phi E divided by 2, right? We don't have to do this case because this was the parameter value that we were finding at the face, but here now you directly have the velocities and values of the parameter at the face itself. It's stored in the face itself, right? So that was the Halo-Welch staggered grid, which theoretically solves the problem, but then there's another problem, that this is computationally heavy. Why is it heavy though? Well, it's simple. You have stored it at different locations, so when you are finally running iters or solving, you have to um, account for all these different locations, right? So computation is a very heavy job, and that is why what modern CFDs currently use is what we call the collocated grids, but with a Richow interpolation. So I'll come on that. So what currently modern CFDs use is your, okay, let's use the pen, is your collocated grids with Richow interpolation. So it's just a very logical solution for normal collocated grids that we had. So what are collocated grids? Collocated is technically just the normal grid that we were talking about. So where everything is stored at the cell center. So you have um, phi that can be P, V, U, and W, rho, everything stored within the cell center itself. So that was how we were working on earlier. But as we told, the problem was it was um, the checkboard pressure case, right? But here now what the engineers came up with is the Richow interpolation. So Ri and Chow, two different people, they came up with this idea that you can add a pressure correction term, right? So what it does is, let's take this. So here you can just take kind of an like you can just imagine like something like an upwind concept, or like the first order upwind concept flow. So without Richow, like if the pressure was 100 0 100 0, that is your classic checkboard pressure case, this would be the case, right? But with Richow, you have a pressure correction term, because of which you will get pressure like this, so it's distributed, right? So now this makes sense, right? So if there's a flow and there's velocity, there's water moving at a certain velocity, so the pressure keeps gradually decreasing or gradually changing. So now how the pressure changes is not something that we have to worry now, but it's changing, right? It's not that the pressure exists but there's no velocity, as we had seen in the normal collocated grids problem. So with the addition of a pressure correction term, so it's like a plus Rp. So this Rp is just a correction term that is added so that you don't fail under the checkboard pressure case, right? So this is what modern CFDs use. So modern CFDs use this, that is the reach or interpolation. So I'll just go back and explain all of them once again. So you had normal grids first. So you had normal grids first, where you had all data's all parameters values stored in the cell center itself, everything that is P, V, U, W. But the problem with this was the checkboard pressure case, where you had alternate pressures. And what was wrong with it? Well, so when you compute velocities at the face, so if I'm taking this face, you take it as an average of the two. So then you get suppose 0.5, and you do it for same for these two grids, you get 0.5. So when you take the gradient, that is delta P, you get equals to 0, which means that velocity is also gonna be nearly a constant or a 0, which is not possible, because of which we have to do some corrections. So that's when we went to the staggered grid, the Harlow-Welch staggered grid, where you saved the location. You stored the value of pressures at the cell center, and you stored velocity values at the edges of the cell or the control volume. So you had pressure here, pressure at the cell center, and you had velocities. These were velocities at the cell edges or face. So here you directly compute the value from the face itself. So since the velocity is already stored at the face, you don't have to use any interpolation to find the velocity at the face, and you directly use that for computation. That again evades or completely eliminates the problem of checkboard pressure. But again, that was computationally heavy because you are storing data at various places. So when you are aggregating or integrating all of them, it is very tough. So then engineers came back with the collocated grids, but with an addition of the reach or interpolation, where again all the parameters are stored in the cell center, but now you have a pressure correction term that is given by the reach or interpolation. There's something that goes on back end that you have a correction term, because of which it gets distributed. So the checkboard pressure doesn't exist anymore. The pressure gets distributed, and so modern CFD now use the reach or interpolation, the collocated grid with reach or interpolation. So why was collocated grid more preferred than staggered? Because it's way faster, right? Because all data is stored in the center of the cell itself, and you can just take it from it directly, right? You don't have to compute anything else. You don't have to compute for other locations. Phase, you can just compute at the face with the reach or interpolation that is standard for all phases. So this reduces the computational time because you're getting all the required parameters from one location itself, right? So that was about grids. So hope you understood the normal collocated grid, staggered grid, and collocated grids with reach or interpolation. So now we'll jump on to now we'll jump on to the few types of solvers that are used currently. So the first one is your SIMPLE, that is the simple. So again, these are all used to calculate the pressure and velocities. So you had earlier, just before this, I'll just give an insight of what was happening. So yeah, just before simple. So yeah. Okay. So we had upwind. So you had FOU, that is first order upwind and second order upwind going on. Then you had your quick. Then you had MUSCL, and you had TVD, that's total variation deviation. So these methods were used in order to find the phase values, right? So using these methods, you used to find the values at the phase, correct? So if there was a grid like this, was the value over here, if there were 2 points at the center, that is P and this is E, then in order to find phi E, you used to use all these methods. Now what these methods that we are gonna uh, cover up now, what they do is they find pressure and velocity. So these are pressure velocity coupling solvers, right? So what is their job? It's just simply to find the pressure and velocity, and then with that uh, go on for rest of the solvings, right? So what simple does is, I'll first expand this. So this is semi implicit method for pressure linked equation, right? So the semi implicit method for pressure linked equation. So what is implicit? We'll be checking on that once we go, but implicit in short means that you're taking future values uh, into consideration while calculating the current value. So it's like if you're finding in, you use in plus 1 as well. So this is what implicit methods mean, but we'll check up on that later. So what does simple do? So this we had discussed earlier when we were talking about pressure based solvers. So when we are talking about pressure based solvers and segregated pressure based solvers, under that we had taken SAI, MPL, I mean simple as the example. So what it does, number one step, guess a pressure. So it guesses a pressure, let's say P star. Okay. Next, what it does is that it solves for the momentum equation. So it solves momentum equation. So what do you get with this? You get U star, V star, and W star. So you have got three velocities now. Go there, right? Yeah. Now number 3. So you've got the velocities. Now you check for continuity. Check continuity. So you substitute in the continuity equation, and then you check if satisfied, else how far is it from satisfying, right? You check this. Now based on this you come up with a correction term. So you come up with pressure correction term or pressure correction equation. So you solve such that you get a term P dash, right? That is the correction term. Now you correct the pressure, so you put it, you get corrected pressure is equals to your P star, that's your initial guess, plus P dash, that is a corrected pressure term. So the correction, then with this now you correct velocities. So how do you correct velocities? Again, you put it in the momentum equation, so you get corrected velocities, that is U star, you get a new U, so U is equals to U star plus U dash again. Okay, so you check how far it is from the continuity equation, and you do this, you correct pressure, and then using pressure you correct velocities. Then you repeat the same process until residues are small. So residues are small. So what are residues? So residues technically means you can just for now you can kind of say it's the error or how far it is from converging. So once you reduce your residuals, so residuals means that your residuals, not residues. So residuals, that is residuals. So these residuals are like kind of errors you can imagine. So once they are less, you can say that. So if your error is less, that means you're more accurate to the solution, right? So that's what it means. So you keep iterating until your residuals are small. So I'll just repeat all this again. So you first guess pressure. So once you guess the pressure, you solve the momentum equation using this pressure. So you put the delta p term, so you substitute here. Then you solve for momentum equation, you get v. Then you put the v in the continuity equation. So you have your dou rho by dou t plus del uh, del v, right? Del v is equals to 0. So you put it in here, you get a solution, and then what is left? So del did I there's a del rho, right? Del rho v is equals to 0. So you put the v over here, you check if it is satisfied. If it's not, you check how far it is from getting satisfied. So using that, you make a correction equation for the pressure, and then you find the correction term p dash. So this is why I said that pressure is the correction, is the control factor for velocities. That's why they are supposed to be connected, or that's why they have to be coupled. So you correct the pressure, then you correct velocities by adding the correction terms, and then you repeat this whole process until the residuals are small. That means until you get, suppose the actual solution for this is v, and at v100, that is the 100th iteration of v, you get v100 almost equals to v, such that when you replace it in this equation, you're getting the equation as 0. That's when you can say the residuals are small, or the solution is finally converging, right? So it's not necessary that if a solution is converging, it is actually true. So converging means you're just getting consistent results. So until residuals are 0, you cannot tell if the solution is correct, right? So you have to repeat this whole process until the residuals is 0. So this was your number 1, that is simple. Now number 2, oh my god, yeah, number 2. So you have simplex. So simplex, or simple C is what I like to call it. So simple C is just the same, but they use better approximations for velocity correction. So the results, so it results in more accurate pressure. So what does this mean? So there was this equation, right, which I had told you, that is P is equal to P dash plus P star. So P star is the assumed pressure that we did initially, and P dash is the correction term. So in simple C, you use a better equation for this correction term. Hence, you get a better value for pressure. I mean, you first correct the values of velocity, and then using the control factor, that is pressure, you get an even better correction term for pressure, because of which you get a better accurate value for the pressure, right? So in short, you get the residuals are the residuals become smaller at a faster rate than the normal simple method. So then after the simple C, you have your simple R method, or the simpler method. So third is simpler. So here they just compute a better pressure field before correction. So again, this is just based on how you're correcting pressure. So here you have another way of correcting pressure, that is by computing a pressure field. So there's like a domain range that is calculated, and based on that, on this domain, so you correct the pressure. So you are like constraining values such that you converge, or you lessen the or you decrease the residuals at a faster rate, right? So again, decreases residuals at a faster rate. So that is about all these 3 methods. Now there's one more which works a bit different. So that is your piezo So fourth one is your piezo method. Again, this is highly used now. So this is pressure implicit with splitting of splitting of operators. So what does this mean? So this is first of all mostly used for transient flows. So what is transient flows? Transient flows are flows where your time changes. So it's time dependent flows, time dependent. And what's the opposite of it? Of course, the steady state flow where it's independent of time. So the flow behavior doesn't change with time. But piezo is used for transient. That means where the flow behavior changes with time. So how is it different? So in simple, what we did is we had one correction per iter, right? Per iter. In piezo, you have multiple corrections, right? So what does it mean? So it means that you have, suppose you were doing this, right? So p1 is equals to p dash plus p star. So it computes more of them. So p dash 1 plus, sorry, p dash 2 plus, I'll write it as p dash 1 plus p star. So p star remains the same. P3 is equals to p dash 3 plus p star. So you have multiple equations for corrections and it keeps correcting multiple times. So that's why this, in this method, the residuals reduce much faster, and hence it's used in transient flows, because usually solving a transient flow, you usually go with a coupled solver, but when you're using a segregated solver, you won't use simple, you would rather use piezo because it reduces the residuals much faster, right? So that is all about the segregated solvers in the pressure velocity couplings. Now you have another type. This is not a type. Till now we were talking about segregated solvers, right? So what is segregated? I talked about this before. So segregated is when you're sequentially solving for P, U, V, and I don't know what, W and rho. So next that you have is the coupled. So in coupled is this normal. We are solving U, V, W, P, rho simultaneously, right? And this is by creating a huge matrix, and then you have matrix solvers. So that will talk upon later. So with this they compute the values of P, W, U and V. So all the correction, everything goes on side by side. So it's more like a parallel computation that happens. So this is mathematically or computationally heavy in the sense that it takes a lot of power, but then it's computationally much faster, like around, I don't know, around like 1,000 times faster. It's not like an exact number, but okay, let's write it as much faster. So much faster than segregated, and that's why most of the time you use a coupled solver. But of course you cannot use coupled for all cases. You have to use segregated for many conditions as well. So yeah, that was all about the pressure velocity coupling and its solvers. So now next that we'll be touching upon is solver technology. So yeah, we'll just check on solver technology right now. Let's go. So the next topic that we are going to cover here is solver technology, right? So this is now where we are going to talk about two types, that is your implicit solver, and two, your explicit solver. explicit solver. So what does each of them mean? So in your implicit solver, okay, first I'll talk about explicit solver. So explicit solver is your normal, how you would solve an equation, that is your future depends on known values, known past or present values, past slash present values, right? So I can just write a general equation of, like, suppose un plus 1 equals to u times n plus delta t times RHS. So here what this means, RHS, again, what I mean by this term is just RHS, right? So here I can say, suppose n. So what it means is it just depends on anything that is already known to us, right? So there's no other future terms. Now if I talk about implicit solvers, it's just the opposite. So your future depends on future. Just remember it like this. So just take the general equation of un plus 1 is equals to un plus del t RHS n plus 1. Well, how is, so this is your technically the future part. So as I told, your future value is depending on present, of course, plus the future value. So how is it possible? So when you're doing a matrix, like if you're doing a coupled solving, right? So usually matrix handles all values parallelly, right? So that is why you use implicit, I mean, that's when you have this idea of implicit solver. So why is this important to know both of this? So, well, it's just that they have like some conditions. So it's like this is simple and fast, but stability, you have some restrictions, stability restrictions. In implicit solver, that is, it's, so you have huge time steps possible, huge time steps possible, and it's stable, but it is more computation, and you need more memory, right? So of course you need more memory because you're calculating on the all future values together, and then you're trying to figure out the present values based on that. So uh, so yeah, this is what implicit solver and explicit solver mean. So this is when it's the right time to know what your CFL actually means. So CFL, as I discussed earlier, is your current Friedrich Lewis condition. Just increase the thickness condition. So this is the CFL condition that we say. So this is usually equals to your u delta t divided by delta x. So what does this mean? It says how far information, that is info, travels in one time step, right? So suppose I have time step, I want to know how much, suppose how many meshes the information skips at one time step. So if it is 5, suppose CFL is 5, that means at one time step the information covers 5 meshes, right? So 5 mesh elements. That is technically what your CFL says. So why is CFL important? Well, because now if your CFL is too large, so if CFL is high, means you're skipping data, right? You're skipping over cells quickly. So info jumps, right? So this means it's more chaos. So it's usually you avoid high CFL, and if CFL is less, it means it's normal, right? So it's just not skipping, it's going normal. So doesn't skip much values, much values. So now if we can generally talk about this, so now can you say uh, which method will have what type of condition for CFL? Well, let's just check on that. So if I'm talking about explicit solvers, so explicit solver, you don't know the future, right? So you just can't jump. So in case this was my time steps, right? In case this I have like suppose 5 CFL as 5, I jump over here, but I don't know the values of these, and explicit solver requires you that if I am finding the value of this, I need to know the value of these, right? So if I have already skipped these cells, that means I don't know these values. So from this cell to this cell I skipped without knowing these values, then the explicit solver cannot calculate these values because it is dependent on the past cells, right? As I told here, un plus 1 is equals to un plus delta t times RHS of n. So this it's dependent on the past values and the present value of the cell, right? So you cannot have CFL, or rather I would say for explicit solvers your CFL has to be less than 1. Is one very important condition for explicit solvers. For implicit solvers, as I said, let's take the same example. So you're skipping, so from this cell you just skip the data and gone here, but in your implicit you know you're calculating the value of this by future itself. So it doesn't matter how many values you skip over here in the past, the value is determined from the future itself. So there is no CFL condition as such for implicit solvers. So you can have like CFL even equals to 100 or 10 or like 50 or 10, yeah, anything like that. That means it can skip 100 cells at once, but then at one time step. But again, that's only for implicit solvers. So yeah, that's why CFL is a very important condition that you are supposed to know. So hopefully that's understood. So in short, it means how much information or how many cells you're skipping per time step. Now going on to two other types. So this is, if anyone has ever touched fluid mechanics as such, so you know it's, you have steady solver, and you have transient solver, transient solver, right? So what does steady solver do? It it solves when the state of flow is steady. So that means no change in fluid behavior with respect to time. This is exactly what steady state means. So example, I can just take it as, I don't know, pipe flow or heat exchange, right? And in transient, it flow behavior changes with time, or it is dependent. Well, it's right in brackets, it's dependent, it's time dependent. So that's why you use transient solvers for these. So example can be, I don't know, combustion, or your vortex shredding. So more, almost everything of turbulent models are transient solvers. You need a transient solver for solving your turbulence. So yeah, so hopefully that's understood, right? So now why did we have to learn all of this? So now it's just very easy for you to select what type of solvers you need for what type of uh, condition or what type of project that you are undertaking. So now I don't know, just for example, if I take, let's say, let's take example, first example is pipe flow, right? So here I'll take pressure based, of course, right? pressure based solver. Why? Because my Mac is going to be less than 0.3, density will remain almost constant. It's going to be an incompressible flow, the constant. So you'll use a pressure based. Now next, will you use a segregated or coupled? Usually you'll use a segregated type for this, segregated. Then here will you use implicit or explicit? So mostly in CFD, current CFD, you just use implicit forms because it's much stable. So use implicit. And here, do you go with steady state or transient? Of course, it doesn't change with time. So you go with steady state solvers, steady state, and then you can either use a simple or simple C, but we can just use a simple solver. So what are these solvers used for? Simple. So that is used for your calculation of P, V, W, V dash rho, right? Sorry, U, P, V, W, U and rho through pressure coupling, right? And now for calculating phase values, you can use any concept, either FOU or I don't know, you can use SOU, and you can use Q by CK, but this is mostly for transient flow, so we'll avoid this for pipe flow. You can just use FOU or SOU, right? Or you can use just a TVD, total variation diminishing. So again, now since you have an idea of all of these, you can now know the backend of what's happening, right? So now you can select solvers or models based on the knowledge that you have gained from this past sessions and today's session. So that is why all this was important. So also, it's usually just name important point. It's usually preferred that you use FOU for first time convergence, and SOU, the second order append, for final convergence. Because SOU might cause, the rate of divergence in SOU is usually a bit higher. So what you do is you first converge, you use FOU and try to converge it. Once you have reached that first time convergence, then you use an SOU, that second order append, to finally converge it, right? So yeah, this is just something that you need to remember. Sorry, I mean, this is just a general idea or advice. It's not necessary. Because right now in ANSYS you don't choose that first you go this and then you do this. Usually it's just you just go with an FOU directly or an SOU directly. There's nothing that first you do FOU then an SOU. Sometimes solvers internally have this idea of first running FOU and then SOU, so you may not know it in the front end, but back end this itself goes around. But yeah, this is an idea of it. So this is for pipe flow. I'll just take another example. So let's say you have a rocket nozzle, let's say. Rocket nozzle. Okay, I'm sorry. So you have a second example. You have rocket nozzle. Now you can tell it yourself. So pressure, are you going to use a pressure based or density based? Density based. Why? Because the gases expand, so your incompressible flow. M is greater than 0.3, of course. Now next, so will you use a coupled or a segregated? Coupled. So density usually just comes with coupled. There is no segregated for density. You just, whenever you go for a density, it's just automatically just think it as coupled. So because you have to solve for turbulence, so it's faster. Because as soon as you go for incompressible flows, there is high chance that you are encountering turbulent flow. So now here you will go implicit. As I told, right now it's only implicit that usually you go with because it's steady. Then here again you can choose either steady state analysis or transient. Transient if you want to know the turbulent features, so how it's going to mix up, you can use this. Again, if you are adding with species, so what was species? Species is when I told this concentration of chemicals. If you're just doing it with air, you can just do a steady state. So the properties doesn't change much with much with time. But yeah, it's up to you. You can go transient if you want like a very detailed, or you can go steady. So that is up to you. This is something, now you have a knowledge of which type of solver to use when, and which state or which type of condition to go with which type of problem statement that you get. So this is why all this information till today's session was important. So now you know how to set up your uh, CFD analysis, right? So now we'll be jumping on to linear algebraic or linear equation solvers. So now we are done mostly with the physics modeling. So I told, right, this you had nature. So you have nature, you have physics modeling, physics, then you have mathematical modeling, physics model, maths model, then you have numerical solvers, numerical solver, and then you get solution, right? So yeah, we are done with the physics model part of it. Now we'll jump into the maths and numerical solver, right? So that will be done from the next session. And yes, that is all for today's session. Thank you, and if you have any doubts, just put it down in the comments or DM me on LinkedIn at Kashyap Binu. Thank you.